Bismillahirrahmanirrahim. Assalamu alaikum and welcome back. In today's session, we want to talk about experimental design. We've seen earlier that experiments are the bedrock of the enterprise of scientific inquiry. We need experiments to validate ideas. However, we would see that it is possible that we do a lot of experiments while learning very little about the thing that we are studying. The aim of today's session is to talk of good practices in experimental design in which we can learn maximum information about the thing that we are studying while requiring minimum resources in time and in experimental runs. So the important point about experiments is that it allows us to understand the world around us in terms of cause and effect, because this is a natural way of reasoning that we employ to understand the world. So all data is not created equal in this slide, because you can have a lot of data, but you cannot establish any causal evidence from this data because of poor design. You may have a lot of variables that are uncontrolled. So in previous sessions, we've talked of nuisance variables or confounding variables, variables that impact the validity of the conclusions that we draw from a study. So firstly, to highlight the importance of experiment, I would reiterate a quote by Richard Feynman that we've earlier also talked about in this course, and he says that the fundamental principle of science, the definition almost, is that the sole test of the validity of any idea is experiment. So it does not matter how brilliant someone is, if his or her theory does not match with the results that we get from experiment, then that theory is wrong. So that is a basic premise, that we rely on empirical evidence to decide on the validity of ideas and of hypotheses. The other important idea, which is conveyed by the second quote by Robert Hooke, who said that if you want to establish cause and effect relationships, you must do this with a properly designed experiment. So in contrast to a properly designed experiment, you can have an observational study in which you are seeing how different variables are related to each other, but you are not actively manipulating these variables. Because of this, and if you do not control for external variables, the external variables may confound the results that you get. In other words, it may seem to you that the two variables are related to each other, and you may even, jump ahead of yourself and think of a causal relationship that one variable is causing the other variable. However, that may not be the case. In fact, both the variables may be the result of another variable. And we have seen examples of spurious correlations in which two things are associated, but there may not be any direct, causal relationship between these two. In fact, we saw many examples of this. So to avoid this, that we extrapolate and infer causal relationships that do not exist, we need to do proper experiments with a proper design, rather than just an haphazard way of doing experiments in which we are not controlling external variables. But even if we want to do a properly designed experiments, the traditional way of doing this is what is known as a one factor at a time design, in which you hold everything constant and you keep on changing one variable at a time, and you try to optimize on the basis of this. It has been shown at least 80-90 years ago that this thing is not optimal. And in fact, you can have similar results having the same preciseness, the same precision, with a lot lesser number of experiments. And this is done by using a careful design in which you change multiple factors at a time. but not in a haphazard way, but in a very well thought out way. So now, after introducing the need of experimental design, let me outline the remainder of today's session. Initially, I want to talk about motivation. I'm going to build upon the things I've discussed and talk more of why do we need design of experiments. I'm going to talk of the history of design of experiments, and I'm going to talk of some basic designs. And lastly, I'm going to discuss some basic terminology, and we'll be concluding this session with an example of design of experiments. So let's start by discussing the basics of experimental design. So one thing that I've already alluded to is that if we want to make proper causal inferences, for example, in network performance evaluation studies, we want to relate different factors. We may be interested in seeing how different input variables affect on the output variable that we are interested in optimizing. So the best way of doing this is through active manipulation of the variables, that you first of all control the variable and see how the second variable behaves. This is known as design of experiments, and this is an active way of creating data. Up till now, we have been assuming that we have been provided data through some external mechanism and we are to analyze this. But now we turn to the question of how to create data that lends itself to efficient statistical processing. So to recall an example that we have already discussed of spurious correlation, we discussed that the size of the feet of a person and his or her verbal skills are correlated. Studies have shown that if your feet size is larger, you have better verbal skills. But if we just base the conclusion that we are going to draw from this, that having larger feet gives you better verbal skills, we must consider what are the other variables that we've not considered. So an obvious external variable is the age of that person, because obviously children have smaller feet, adults have larger feet, and adults also have better verbal skills than children. So it may be that this is the confounding variable which is producing the effect of which is showing in the association between feet size and verbal size. There may be many other factors as well that we're not considering. For example, the reading habits of that person is also a variable that actually helps us determine the verbal skills that person has, how much education that person has. Has he or her gone to college? What is the education level of their parents? So the question is that because of all this hidden variables, we cannot really establish any causal relationship. We cannot say that larger feet gives you better verbal skills, or even the other way around. If we want to establish any causal relationship, we have to do a properly designed experiment using the principles that we are going to expound in this session. One important area in which design of experiments is used is the area of epidemiology, the area of medicine, in which we study if some medicine has some healing property or not. For example, does using aspirin improve your health? So this actually cannot be decided just on the basis of a purely observational study. To actually determine this, we have to take care of all the external variables, things like the sleep duration, the gender of the subject, the diet that person takes, and also what other drugs that person is taking. We must take care of all these external variables and then decide the question or the hypothesis that we're considering, that does taking aspirin improve your health? And you have many other examples, like does smoking cause cancer? Does exercising lead to improved health? You may say that exercise leads to better health, but you also need to consider all the other variables. It may be that certain people are genetically predisposed to good health, while others may be genetically predisposed to poor health. So it may also be that if you are healthy, then you tend to exercise. So I hope I've conveyed the idea that if you want to make causal relationships, and those are very important in policy making in network performance evaluation studies, we must use design of experiments. And all experiments are designed. Unfortunately, many experiments are poorly designed. And the idea of the lectures on design of experiments is that we learn how to do efficient experiments in which we learn the most using the least resources. So let us now talk about where design of experiments are used. Traditionally, design of experiments were proposed in the area of agriculture. So there is a very famous statistician, Ronald Aylmer Fisher, who is actually the pioneer and the creator of the discipline of design of experiments. And he proposed design of experiments specifically in an agricultural setting. He was the chief statistician of an agricultural station in Britain at a place called Rothamsted. And at that place, they were interested in seeing how different fertilizers have an effect on the yield of a farm. So they were doing and conducting experiments for a very, very long time before Ronald Fisher joined them. And when Ronald Fisher joined them, they gave him, huge troves of data, and they said, okay, go and analyze this. And one conclusion that Fisher drew from this was that the volume of data is not important. In fact, you can have a lot of data, but which may be useless for inferring any property about the thing that we are studying because of poor design. As an example of how this affected in agriculture, Fisher noted that fertilizers were being compared, and they were actually used in different years, in different weathers, in different fields. And the variation because of these factors was far greater than the effect due to fertilizers. And because of this, using a term which was proposed by Fisher, the effects were confounded. In other words, we were mixing the effects due to weather and the effects due to the treatment of fertilizers. And there was no clear way of differentiating that what is the effect of the fertilizer and what is the effect of all the extraneous variables. So this was around 1920s, and Ronald Fisher also proposed many fundamental ideas of design of experiments that are even used today. For example, he proposed randomization, a method of randomizing so that the effect of all the extraneous variables is averaged out in some sense. He also proposed factorial design, in which you do not just change one variable at a time, you change multiple variables, but according to a very careful plan. We'll be talking more about that later, but let us now talk of the progression of the discipline of design of experiments. It initially started in an agricultural setting, but then in the 1940s and 50s, it made a big splash in the industry as a process optimization tool. And one pioneer who was very active in this area was George Box. And we'd be hearing a lot about Ronald Fisher and George Box when we discuss design of experiments. George Box was primarily a chemist, and he wanted to improve certain chemical industrial processes. And he worked on the application of the principles of design of experiments to an industry setting. And the two settings are different because agricultural yields take a lot of time to mature and to actually show results. Whereas in industry, the environment is different. So George Box was also son-in-law of Ronald Fisher, actually imported the ideas and used those ideas for improving industrial processes. And this was then extended in 1960s and 70s, the time in which statistical quality control and things like Six Sigma really took root. So one person who really made a difference in this regard was the American statistician Edward Deming, who was very active in Japan. And because Japan was doing a lot of work on improving their industry operation, Deming actually showed that even in the face of variable input factors, you can produce a product that is robust to these changes. And because of that, we now have examples of very good quality, robust products from Japan. So, for example, the Japanese cars are very famous for being very robust. They are having very little variability, so they tend to work very well. So design of experiments can also be used to produce very finely controlled, high quality products. And Deming was one of the most important players in this area. So many of the things that we are going to study in the topic of design of experiments is taken up forward by things like Six Sigma, in which the focus is more on the quality side. We are only going to scratch on the surface of design of experiments, and we're going to talk of how this discipline applies to network performance evaluation study. And my aim is to give you an understanding, a broad understanding of what the field is and how it may be applied. But to really understand any of these things in more depth, you would need to do subsequent study by consulting textbook or taking other courses. Design of experiments is not limited to these three fields. So not limited to agriculture, not limited to industry, or to settings of quality control, but they are being used extensively in the modern world. For example, it is used in website design, because in website design, you may have a lot of different factors. So where to put the banner, where to put the button for signing up, where are the other options. And in fact, it has been studied by website analysts and also psychologists that even changing minute differences where the different things are placed can actually create a lot of difference for business. In fact, it was studied and shown creating a difference in the contrast of the sign up button, it actually produced a difference for one company. So how do we discover what is the best website design? In our case, in network performance evaluation study, it would be how do we discover the best values of the different input variables to optimize on some response variable. It may also be a question of how do we compare different protocols or different products and decide on which product is the best. In this case, in website design, the idea is that you have multiple versions of the website and you give that website to a different component of your audience simultaneously, and you control for external variables, covering which will not be in the scope of today's lecture, but the general idea is using experimental design, you can discover what is the best design for your website. And this is just one of the area in which design of experiments is used. It is extensively used also in business, because when we're trying to optimize on industrial settings, even a small change can lead to large savings in the long run. So to highlight the importance of using design of experiments, I will give you a quote by George Box, who is an American statistician, and he's talking in the context of the industry in his country, because there was a big debate in America that why has Japan taken over America in the quality of products. And that was because Japan was, more forthcoming in accepting good statistical practices for creating robust designs. And this is what he said about design of experiments. For there are hundreds of thousands of engineers in this country, and even if the 2⁵ design was the only kind of design they ever used, and even if the only method of analysis that was employed was to eyeball the data, this alone could have an enormous impact on experimental efficiency and the rate of innovation and the competitive position of this country. So this is coming from an authority in this area, and he has talked of a very simple design, 2⁵ design. We'll be covering this in the forthcoming sessions. For now, this is a design in which we compare 3 factors, 3 input variables, and each of these 3 input variables can take 2 different settings. So using such a simple design, and we'll be seeing that this design is not very complex, we can actually do a lot and learn a lot and improve a lot. And that's the basic idea, and I hope I have conveyed the importance of design of experiments to you. So let us now talk about how are design experiments used. So what questions do we answer using design of experiments? So the first thing is we want to build a model for a process for optimizing that process. So this is how design of experiments is used, and then using a very careful manipulation of different factors, we decide on what is the best design. So this is one way. The other important way in which design of experiments is used is to answer questions about hypothesis testing. We've already talked of hypothesis testing, in which we initially form a hypothesis and then we perform a statistical test to see if that hypothesis can be rejected. If you have results that are very extreme under the null hypothesis, you then reject the null hypothesis and you adopt the other hypothesis. So to actually do a good job at hypothesis testing, we need to do design experiments. And to highlight this, I will give you an example that has a very special place in the history of design of experiments. This is a very trivial sounding experiment, but this was actually used, and this actually happened in the life of Ronald Fisher. So here goes the example. It was an afternoon setting in the Rothamsted station, and they were having an afternoon tea, and Ronald Fisher was there. And he offered tea to a fellow colleague, a lady colleague, and Ronald Fisher offered this tea to her, but the lady refused, saying that she prefers that milk is poured first into the tea. So this actually confused Fisher a little, in that Fisher thought that, how is it possible that someone can differentiate between the two? But when the lady emphasized that she actually can predict the differences, then Fisher, being a very astute statistician, got going in his job. He conducted a statistical experiment to verify the claim being made by the lady. So this is an example of a hypothesis test. The null hypothesis in this case would be that the lady cannot differentiate, because this is the status quo and this is what people expect, that you cannot differentiate. And this is what Fisher had in his mind before all this episode. And Fisher wants to reject this hypothesis only on the basis of very strong evidence. So how do we go about this? So the experiment Fisher came up with was, he would present 8 cups of tea to this lady, 4 of which would be milk first and 4 of which would be tea first. And then the lady has to guess, which order the things were poured. So if the lady is able to predict all the 8 cups correctly, then this should be sufficient evidence to reject the null hypothesis. In fact, this is a classical case of a binomial setting in which the probability of getting all the 8 guesses right, in which the probability of each guess is 1 by 2. The probability of getting all of the cups right is just 1 by 70. And because this is a very small chance, if this thing happens, we can reject the null hypothesis and accept the alternative hypothesis. So this is about the experiment which was discussed by Fisher in his own paper on this subject. But it was, related by other historians that actually the lady got all 8 cups right. So this was a very simple experiment, but it highlighted how hypothesis testing may be used in real settings. It also highlighted many of the important principles which were later developed and proposed by Fisher as his theory of design of experiments. The first idea is the usage of randomization. Because if there is a predictable way of either pouring milk first or pouring the tea first, then the calculations that we used do not apply. And also randomization is important because all the 8 cups are not going to be exactly alike. You can think of many differences between them. It may be that in one cup you have more sugar poured in, and effectively you would have differences in sweetness amongst all the 8 cups. It is simply not possible to have identical conditions in all the other variables. The temperature may vary. For all that we know, when we have 8 cups, you may also be using different tea bags for creating those teas. So these are all examples of extraneous variables which may actually tip off the lady in this question about what is happening. So we need to have a randomization method. And it's very important to emphasize that this randomization is not a haphazard kind of a randomization, or not what humans would think as random. Because we have seen in earlier sessions that humans have a very tough time at being random. So we usually have devices, special devices for creating random occurrences. For example, we may flip a coin, or we may use tables of random numbers that have been published. But in either case, you cannot simply haphazardly decide. You have to have a good way of randomization. Another principle that can be used here is the principle of blocking. So as an example, I said that you may be using different tea bags. In that case, it is important that we only compare alike things together. So if you're using one tea bag for 4 of the cups and another tea bag for the other 4 cups, it's important that we make different blocks, and the alike cups are kept together, and we randomize within that block as well. So all of these things would come later, but the idea is that even using such a simple experiment, we can understand about the ideas of Ronald Fisher as he discovered this field of design of experiments. Let us now talk about some basic experimental designs. So one way which is often attributed to Thomas Edison is known as the trial and error method, in which you try different options and try to come up with the best possible combination of factors. So we will give more credit to Thomas Edison, who was a very prolific inventor. He created lots of devices and instruments, and he has many patents. So his method was not limited to trial and error. He actually himself talked of his method, and I will quote, "When I want to discover something, I begin by reading up everything that has been done along that line in the past. That's what all these books in the library are for. I see what has been accomplished at great labor and expense in the past. I gather data of many thousands of experiments as a starting point, and then I make thousands more. So he himself says that he used thousands of more experiments. But the idea is that through properly designed experiments, you can actually learn a lot while doing, quite a lot less than 1,000 experiments. In fact, in most practical settings, we are doing just 4, 8, or 16 experiments. Or if we extend a little, 32 experiments. And we can learn a lot about, whatever we are considering just in these number of runs. So while Edison, used proper designs as well, but he resorted to trial and error when he could not, determine the theory about something. He just simply resorted to trial and error. So this is not the most efficient way of discovering things. The next progression was what is now known as one factor at a time design. In one factor at a time design, you start from some default setting and then you keep on changing one variable at a time and you observe the response. So based on this, you actually make different changes and you decide on the best operating point. But the drawback in this is that it is possible that you do not get to an optimal setting. We would see that this is very much possible in one factor at a time design because you are constrained by making these choices. Once you decide on a choice and you change that factor, you cannot revisit that choice again. And also in one factor at a time design, you miss the interaction between factors. So as an example, if you see on the slide now, you have two factors, factor A and factor B. In fact, both these factors can take two different levels. So abstracting those levels, we call them low and high. So these would be then categorical variables that can take two levels. So we see that we would be conducting experiment at the low setting of factor A with low setting of factor B, and then we would be changing the factor A setting to high while keeping the factor B setting constant at low. And then we'd be comparing which one is the best point, and then we'd be deciding on which factor to change next. The point here is that it is very much possible that we can miss interactions between different variables. An interaction is when the effect of a factor depends on the level of other factors. So the effect of a factor is not independent of other factors, and because of that, one factor at a time is inefficient and also incapable of detecting interactions. If you have interactions in a system in which the effect of a factor also depends on the level of the other factors, if the level changes, the effect of this factor changes as well. If you have that, one factor at a time design can give you misleading results. So in a sense, one factor at a time is like the analogy we saw earlier about an elephant and 6 blind men. So you have different idea about the thing that you are studying depending on where you start from. And we have covered this before. The next progression in the discipline of design of experiments was discovery of the method of factorial design by Ronald Fisher, in which it was shown that one factor at a time design is suboptimal. It can miss the optimal points, and it can also have a lot more runs than are necessary for giving results of the same precision. In fact, he showed that using lesser number of runs, he can give results having the same precision using factorial design, in which multiple factors are changed at a time according to a carefully crafted plan. So from his paper, which was based in an agricultural setting, let me read a quote to you. No aphorism is more frequently repeated in connection with field trials that we must ask nature few questions, or ideally one question at a time. The writer is convinced that this view is wholly mistaken. Nature, he suggests, will better respond to a logical and carefully thought out questionnaire. Indeed, if we ask her a single question, she will often refuse to answer until some other topic has been discussed. So he has a humorous way of saying the same thing, that using one factor at a time design, we can miss on the optimal setting. So how do we go about creating such a multi-factor design in which multi-factors are changing at every step? We will be studying this specifically in other sessions, but you can see two designs shown at the bottom of your slide. The one on the right hand side is what we've just covered about one factor at a time design. The other design is the factorial design. So imagine that we want to, in the factorial design, which is at the left hand side, you would observe that there are 8 experimental runs. This is because there are 3 factors, each at 2 different levels. So there is factor A, B and C, and they can be either high or they can be low. If you have a full factorial design in which you have 2 raised to 3 experimental runs, the geometry of that is shown on the bottom left hand side of the slide now. If we compare this to the one factor at a time design, you also have the same number of factors, the same number of levels of those factors. If we want to have comparable results, we need to have 4 replications at each data point at the one factor at a time design. This is because in the full factorial design, if you observe, you have 4 instances where A is at the low level, and you have 4 instances where A is at the high level. And because of the averaging effect, you get to know about the error, the experimental error, and that is very important. And we often do replication. In other words, we repeat the experiment multiple times at the same factor setting. So if we do the same in one factor at a time, you would observe that we are doing 16 experimental runs, which are twice the number of runs that we would require for a factorial design. In fact, the more number of factors that you have, the efficiency of a factorial design increases furthermore. You can see that in the table on the bottom right hand side of the slide now. If we keep on increasing the number of factors, the relative efficiency of factorial design improves as well. Okay, now we can discuss some terminology about design of experiments, how some specific words are used to mean something technical and specific. So to study about that, let us consider a process in which you have some input variables and you have an output variable. Of the input variables, you can control certain variables, that is, you can change their setting. But there are some other variables as well which may be outside the control of you as the experimenter. So if all of the factors are outside your control, this would be purely an observational study. If all the factors are in your control, then this is a fully controlled experimental setting. In many practical settings, we are somewhere in between. Ideally, you would like to have full control so that you can maintain statistical control of your experiment. You can see how the higher setting of a factor affects the other variable and how the lower setting of that factor affects the other variable. And in this way, you can get better estimates and better conclusions. In other words, you can make better cause and effect reasoning. So let us now more precisely define what a factor is. A factor is also known as a predictor. If you recall our discussion on regression, there we discussed independent variable and a dependent variable. The independent variable was something that you can control, and you are seeing how controlling that affects the dependent variable. The terminology in the context of design of experiments now is a factor. So a factor is something that you can change. Examples in network performance evaluation settings would be CPU type, memory size, number of disk drives, workload used, throughput, and so on. Okay, now let us study what a response variable is. When I talked of throughput as possibly a factor, that meant the bandwidth of some technology. As an example, you may be using 802.11b, which offers a certain bandwidth, or you may be using 802.11, which possibly 802.11b has multiple settings, but 802.11a can offer up to 54 megabits per second. So this then is a factor, because having a higher bandwidth technology can give you better throughput that is actually measured. So let me rephrase the throughput which I used for a factor to bandwidth offered by a technology. Response variable would be the throughput that you actually measure. It can also be the response time or any other thing which you observe as a dependent of the independent variable that you've changed. Furthermore, there is a term known as a level. A level is the different settings a factor can take. So typically, factors are categorical variables and they can take different levels. So as an example, if your factor is the CPU type, it may be the 8080 processor, it may be the latest Intel processor, the latest AMD processor, the i5s, the i7s, and so on. So these would be labels of your categorical variable, and in terms of design of experiments, these are known as levels. आपका factor किन जो levels को adopt कर सकता है. Also, we've discussed example of the bandwidth. So 11 megabits per second, 54 megabits per second can be taken as the different levels for the factor of bandwidth. Also, we usually make a distinction while talking about factors of a primary factor and also a secondary factor, because typically we do not want to study everything that affects the response variable. You are interested in studying a few things. There may be a few other factors that do have an effect on the response variable, but you're simply not interested in quantifying their effects. So these would be secondary factors not considered in your study. The primary factors are those factors that you directly study. So let us now precisely define what a design means. A design is simply the number of experiments, number of factors that you have, the levels that they can take, the number of experiments that you perform on each factor level setting. When we specify all of this, we are specifying the design of experimental design. So we need to learn about a few more terms. The next term is experimental unit. So assume that you're doing a medical study where you want to find out the efficacy of a medicine. Then the experimental unit in this case would be humans, because you are testing this medicine, the effect of this on humans. And those humans may be male and female. You may be doing blocking of these experimental units on the basis of gender, but I hope you get what an experimental unit is. In terms of network performance evaluation studies, our experimental units can be machines to which we are subjecting the different factor level settings to. Replication is simply the repetition of the experiment at some factor level setting. So if we have the same factor and level setting and we redo the experiment multiple times, this would be known as replication. And interaction, we've already discussed, is the fact that the effect of one factor depends on the level of the other factor as well. So if the level of the other factor is changed, the effect of this factor would change as well. Let me now reiterate and in a way wrap up this session by telling you about 4 design of experiment fundamentals which were proposed by Fisher. The first one is the factorial principle. The factorial principle is that it allows the effect of several factors and even interactions between them to be determined efficiently using lesser number of runs than you would require for a one factor at a time design. The other basic principle is the usage of blocking, in which we divide the set of experimental units into blocks of similar units. We just gave an example of the medical study in which humans are blocked into different groups or different blocks. One block would be the block of males, the other block would be the block of females, because you expect that these blocks would differ in some sense. So the aim is that we remove some of the variability from treatment contrasts, and this is important when we want to compare different treatments. The third fundamental principle is the principle of randomization, and that helps us to minimize the effect of extraneous variables. Lastly, the fourth principle is the usage of replication, because the usage of replication helps us get an idea about experimental error, because doing an experiment just once does not let us know if that result is typical. But if we do that experiment multiple times and if we average over that, we get a better estimate of what the real effect is. So one important quote in this regard is by George Box, who says that you should block what you can and randomize what you cannot. Again, as discussed earlier, George Box and Fisher are the two pioneers in this area, and they are building upon each other's work. So quote here by Box is very relevant, that you should try to reduce the variation of and the effect of extraneous variables by blocking wherever possible, and if you cannot block, then you must randomize. Okay, now let me wrap up this lecture by giving you a practical example of how design of experiment can work. For this, we're going to study designs of a paper helicopter, and I've got 2 of them with me, and you can see on the slide as well the basic design of this paper helicopter. This is a very simple paper helicopter in which you have the rotor. This is simply a cut made in the paper according to the design shown on the slide. You can see that the solid line is indicating where the cut would be made. One cut is made here and the other cut is made here. So the top side of this is the rotor or the wings of the helicopter, and this is the tail of the helicopter. What we're trying to discover is, through design of experiments, is to find the best factor setting which will give us an helicopter which, when let off from some height, will descend to the ground in maximum time. So we want this design to be such that the helicopter stays in the air for maximum time. What are the factors in this experiment? So one factor is the length of these rotor wings. The other factor can be the width of these rotor wings. Ye kitna chauda hai. The other thing could be, again, similarly for the tail of the helicopter. Should it be of one size, or should it be longer? Should it be shorter? Should it be wider? So there are many different factors and they have many different levels. So as an example of the length, it can be large length or it can be smaller length. So the length of the wings would be a factor, and the fact that they may be large or small, these are levels of this factor. So we want to determine the optimal setting of these factors. And there are other factors as well. For example, are you applying a weight to the tail of the helicopter? In case you are, then this would be one level of this factor. If you do not have this, this would be the other level of the factor. And there are many other factors as well. You can see them on the slide now. So paper type is a factor, that what kind of a paper are you using, wing length, body width, if you're using a paper clip or not, how are you folding the paper. So these are all different factors, and they are going to have an effect on the result. So the important idea here is that suppose I gave one of this helicopter to someone, and I asked him to go to some other room and perform an experiment. And I gave the other helicopter to someone else, and I asked him to go to his house and do the same experiment. The thing is that because of the different setting, we are going to have many confounding variables. It may be that the temperature of a room has an effect on the flight time, and the temperature at both these places are different. It may be that one person is doing it indoors, the other one is doing outdoors. So we need to do randomization, and we need to do proper experimental design. One way of doing it is to do a block design in which you are throwing or letting go these helicopters from the same height, at the same place, at the same time, in the same method, and then comparing them. And then you compare this for many different factor settings, and then you can make some conclusion about what the best design is. As an example, let us consider these two planes. So I'm going to throw them together. Let's see which one gets to the ground first. So it looks like that we have a winner here, and the design which took longer to get to the ground was this one, which has, let's see what are the differences. It has the width of the wings of this helicopter is less than the width of this one. So what conclusion can we draw from this? The idea is that you cannot draw valid conclusion from just one replication. We need to do this experiment again, and we need to change the different settings, the different levels of the factor, and only on the basis of that will we be able to decide on what the best factor setting is. And that is the general idea of design of experiments. In fact, we're going to study in the forthcoming sessions different design types. We're going to study full factorial, we're going to study fractional factorial. If you have a lot of factors, it is usually helpful to use fractional factorial designs. I'm going to leave this exercise to you to make a paper helicopter yourself and follow through with the designs that we study in later sessions, and I'm sure that you would find it a very good learning experience. Let me now wrap up this lecture by giving you my concluding thoughts. The first thing I want to say is that all scientific experiments are designed experiments. There is no getting around this fact. But some of them are poorly designed. What we want to do is, we want to do good experimental design, because we do not want to do a lot of unnecessary experiments, because if we can have the same information in less number of runs, we should use that design. So the designs that we're going to study next are important tools in this regard. So with this, I would be concluding this session. I'll see you next time, inshallah. Take care. Assalamu alaikum.